You use the cloud services almost every day. When you open Gmail, save a file to Dropbox, stream a movie on Netflix, your data travels to massive warehouses full of servers owned by companies like Amazon, Microsoft, and Google. The cloud computing industry crossed $900 billion in 2025. Almost every business on the planet is moving its operations there. Your bank, hospital, or employer, the apps on your phone. But who is actually responsible for keeping all of that safe? People may assume it's the cloud provider, Amazon, Google, Microsoft. But the answer is more complicated. Because when cloud security fails, the cause is rarely a sophisticated breach. It's usually a misconfiguration, a storage bucket left open to the public, encryption never enabled, access controls set too loosely. These mistakes happen on both sides, by customers who don't secure their data properly, and sometimes by providers whose default settings aren't secure enough. Today, we're going to look at how cloud security works, where the risks lie, and I'll walk you through real cases where major companies got it wrong, mistakes that cost them millions of dollars. Let's start from the ground up. The cloud is a simple idea. Instead of buying and maintaining your own computers, servers, and data centers, you rent them from someone else and access them over the internet. There are three models. First is infrastructure as a service. This is the most basic level. You rent the raw building blocks, virtual machines, storage, networking. The cloud provider gives you the land and the foundation. You install the locks and maintain everything inside. Second is a platform as a service, a ready-made platform for building and running applications. You don't manage the servers or the operating systems underneath. You just write your code, deploy it, and the platform handles the rest. And the third one is software as a service. This is what people interact with daily. Gmail, Slack, Microsoft 365. Someone else builds the software, runs it, and maintains it. You just log in and use it. The provider handles almost everything, but you still control your account, access credentials, and the data you put in. Each model shifts the balance of responsibility between you and the provider. And that balance is the single most important concept in cloud security. It's called the shared responsibility model, and it's where almost everything goes wrong. Here's an analogy that makes this more clear. Imagine you rent an apartment in a large building. The landlord is responsible for the structure, the roof, the plumbing, security cameras, and the lobby. They make sure the building itself is safe and up to code. But once you step inside your unit, it's your responsibility. You lock your own door. You don't leave your windows wide open and don't invite strangers in leaving them alone. Cloud security works almost the same way. Your cloud provider, Amazon, Microsoft, Google, is responsible for securing the infrastructure, the physical data centers, the networking hardware, the foundational platform. They make sure the building is solid, and you are responsible for everything you put inside: data, applications, and access controls. And this is where the vast majority of cloud security failures happen. According to Gartner, through 2025, 99% of cloud security failures are the customer's fault, not the provider's. Not because people are negligent, but because they don't fully understand where the provider's responsibilities end and theirs begin. And no matter what model you use, you are responsible for your data and your access controls. Let me show you what that looks like. In July 2019, Capital One of the largest banks in the United States, discovered that the personal data of over 100 million customers and credit card applicants had been accessed by an unauthorized individual. Names and bank account numbers. Over 100 million records. The attacker was Paige Thompson, a former software engineer who had previously worked at Amazon Web Services. She exploited a misconfigured web application firewall in Capital One's cloud environment. Here's what happened in simple terms. Capital One had set up a firewall to protect their cloud servers, but it was configured incorrectly. Thompson used a technique called server-side request forgery, essentially tricking the server into handing over its own security credentials. With those credentials, she accessed the Amazon S3 storage buckets where Capital One kept customer data. But AWS itself was never breached. Amazon's infrastructure worked as designed. The problem was entirely on Capital One's side of the shared responsibility model. They had misconfigured their own security settings, leaving a gap that could be exploited from the outside. $190 million to settle a class action lawsuit from affected customers, and total is about $270 million because of a configuration error. The Capital One breach was caused by a specific type of failure, but the cloud threat landscape is broader than that. Let me walk you through the biggest threats in the vast majority of cloud security incidents. Misconfiguration means your cloud resources are set up incorrectly. A storage bucket is set to public when it should be private. A database is accessible without authentication. Passwords are getting cheaper, which means it's becoming easier for attackers to simply log into your systems rather than hack their way through. There are two key countermeasures. Multi-factor authentication, MFA, adds a second verification step beyond just a password, like a code from your phone. Even if someone has your password, they still can't get in. And passkeys eliminate passwords entirely, replacing them with cryptographic keys stored on your device. Insecure application programming interfaces. These are the communication channels between cloud services. They're how your applications talk to databases, services talk to each other, and users interact with your platform. If these APIs aren't properly secured, they don't verify who's making requests, and they expose more information than they should, they become backdoors into your entire environment. Sometimes the danger isn't outside, it's already inside your organization. An insider threat could be a disgruntled employee downloading customer data before quitting, or simply a well-meaning employee who clicks the wrong link, shares credentials they shouldn't, or misconfigures a critical system by accident. These threats are exceptionally hard to detect because the person already has legitimate access. Traditional cloud security focuses on keeping outsiders out. Firewalls, encryption, access controls, all designed to stop external attacks. But what happens when the threat is someone who's already authorized inside the perimeter? This is where a completely different category of security becomes critical, and most organizations don't even know it exists. We'll come back to this because it's one of the most important gaps in cloud security today. In April 2019, researchers at the cybersecurity firm D.A.R.T discovered something alarming. 540 million Facebook user records were sitting exposed on Amazon S3 servers, publicly accessible to anyone who knew where to look. But Facebook itself didn't expose the data. Third-party app developers did. A Mexico-based media company called Cultura Colectiva had stored over 540 million records, including account names, Facebook IDs, and engagement data on an Amazon S3 bucket that was configured for public access, and anyone on the internet could download it. You've now seen these real cases where cloud security failed, not through brilliant attacks, but through protection and data leaks prevention mistakes. So what does effective cloud security actually look like? I'm going to break it down into several layers. Think of it as building a fortress. Each layer adds another wall between your data and anyone who shouldn't have access to it. The first layer is identity and access management. This is the front gate. Everything starts here. Multi-factor authentication should be enabled on every account that touches your cloud environment. Admin accounts, user accounts, service accounts. MFA means that even if someone steals a password, they still can get in without a second verification, a code from a phone, a biometric scan, or a hardware key. But here's what I want you to notice. Encryption protects data from outsiders. Access controls limit who can reach the data. But neither of those answers a question. What happens after someone with legitimate access opens the data? An employee with proper credentials downloads a customer database for a legitimate project. Then they email a copy to their personal account, or upload it to an unsecured third-party tool. This is where solutions like Search Informed DLP become critical, because it addresses a gap that organizations don't even realize they have. DLP doesn't replace your firewalls or your encryption. It works alongside them. What it does is monitor how data actually moves within your organization, across endpoints, email, cloud storage, USB devices, and printers. It watches the flow of sensitive information and flags activity that violates your data handling policies. Think about the Capital One case. The attacker accessed S3 storage buckets containing millions of customer records. If a data loss prevention system had been monitoring those buckets, tracking who accessed what, how much data was being pulled, and whether that access pattern was normal, the anomaly could have been flagged before 100 million records were exfiltrated. This approach is particularly relevant because it doesn't just analyze one channel. It provides a unified view of data movement across all channels simultaneously: email, cloud apps, and endpoints. It uses content analysis to identify sensitive data regardless of format, and it can enforce policies automatically, blocking a file transfer and alerting a security team. Even in the cloud, the network is a critical security boundary. Use network segmentation to divide your cloud environment into isolated zones. Your web servers shouldn't communicate directly with your database servers without going through controlled channels. Deploy web application firewalls, WAFs, to inspect and filter incoming traffic, blocking common attacks like SQL injection and cross-site scripting before they reach your applications. Use DDoS protection to defend against denial-of-service attacks, floods of fake traffic designed to overwhelm your systems and knock them offline. Your applications are only as secure as the code they're built on. Scan for vulnerabilities before deployment. This means both static analysis, examining source code for security flaws, and dynamic analysis, testing the running application for exploitable weaknesses. If you're using containers, scan your container images before they go into production. Set policies that prevent unscanned or vulnerable images from being deployed. In a cloud-native environment, patching becomes fundamentally different. Instead of updating a running system and hoping nothing breaks, you build a new container image with the fix applied, deploy it, and retire the old one. This approach means your systems are always clean and current. There's one more concept that ties everything together, and this represents a cultural shift happening in technology today. Traditionally, software development sometimes looked like this. A team designs and builds an application, finishes it, and then hands it to the security team to review. But by the time security reviews the finished product, the architecture is set, the code is written, and fixing fundamental security issues means going back to the beginning. So problems get patched over rather than solved. The modern approach is SecDevOps. Security integrated into every phase of development and operations from the very beginning. During planning, you define the security requirements alongside the functional requirements. What data will this application handle? Who needs access? How will data movement be analyzed once the application is live? During development, security is part of the code. Sensitive data is encrypted in the application layer before it reaches the database. Dependencies are scanned for known vulnerabilities. The cases I walked you through today, none of them involved genius-level hacking. That's why the combination of traditional cloud security tools and data-focused solutions matters. One protects the infrastructure, the other protects the information. You need both, because attackers and accidents can bypass one. They rarely bypass both. The threats are well documented, defenses are known, and the failures are preventable. The cloud security is not optional. It's a critical business necessity. Thank you for watching. Stay safe and secure.